So when we talk about musical instruments, you need to understand that, like, basically the process of how stringed instruments make noise. And how a stringed instrument makes noise is you have a string here, and the string, when you pluck it or strum it with certain instruments, they make a noise. And so when you like pluck an instrument and you use just like a pick, so like you're hitting it at one point, it sends transverse waves out, and then the transverse waves bounce and then they even out, and so then you just create what's known as a standing wave. And when you look at a guitar, when you pluck it, you can see that it vibrates. You can see it going up and down. And so what this is doing, you can see across the whole thing if you pluck it really hard. You can see it. That it only has 1/2 of a wavelength when it's just the open string. But there's these things called harmonics, which when you lightly touch down on a certain area of a string, you get these different sounds. And the cool thing about these is you're not fretting the note, right? When you fret the note, you just get the fundamental note, but on a smaller length. And so when you fret it, it's a different note than the harmonic in the same spot. It's different, it has a different octave. And so these harmonics occur depending on the length of the string. It's a ratio of the length to where these harmonics occur. The nice thing about the guitar is you can actually very easily, seeing on the frets, you can see where they are quite easily. So on the guitar, you have the 12th, you have the 7th, and you have the 5th fret. And you really can't hear them on the phone. I tried. You can't hear them at all. But when you use an amp, and then you turn on the distortion, like, you know how you get that nice rock guitar sound? So just an open note, right? Sounds like that. Then when we fret the 12th, right? Different sound. But then when we play the harmonic on the 12th, it's a different pitch. And then if we get it on the 7th, then we're gonna play it on the 5th. So these harmonics have like this high, almost like a high-pitched sound that people kind of describe as like almost like a ghostly sound. But when you look at a guitar string, you can see that they're different thicknesses, but these do not affect it at all. It is strictly the string length and like tension that affects these. And so it's like, you know, you can just bar the entire thing and play the harmonic. It doesn't matter which string you use. But just to prove to you that it's not a guitar thing, harmonics can occur on any stringed instrument, even if they don't have frets. But when you still like fret the note, it's gonna play at a certain frequency, and same with the open. But when you play the harmonic, it's different. And so it still remains true no matter what instrument you use. So when we talk about strings, right, plucking produces the fundamental, but also when you bow it, let's see if we can, it's the same thing. So if we can find the fundamental, not fundamental, sorry, the harmonic, and then play it, we still get the harmonics can still be played even when you're not just plucking. It's the same concept. So when talking about strings, we have to, get through some like basic terminology. And so this fundamental frequency is what is played on just the open string on the guitar or any other stringed instrument. And so this wave is what you can see in the video that I tried to show you. Is a full wavelength would have this bit. This is considered one wavelength, and this is what's considered the second harmonic. This occurs on the 12th fret, which is like 12.7 inches, produces this first harmonic that we can see on the guitar, whereas then on the 7th fret, which occurs at 8.7 inches, is this second harmonic, and then at the 5th fret, which is 6.5 inches, we produce the next harmonic. And so these increase you get more wavelengths that are being played, even though the length of the string remains constant. You get more nodes, more antinodes that you can see, which at a certain scale, it's physically there, even if in the video you can't see it that well. So now we're gonna work out a problem where we try to find the tension of the string based on basically what we know about the string. And so one of the things that we know is that my guitar is in standard tuning. Standard tuning has this sort of pattern where it goes E, A, D, G, B, and then a small e is usually what they call it. We're going to be working on this big E. This is the thickest string on the guitar. It's considered the 6th string. And so the frequency that the note E is, which more layman terms would refer to as pitch, or if you're in music, is about 82.41 hertz. And so since we're just going to use the entire string, we're going to be working at the harmonic n equals 1. This is really the fundamental note, and which we have the length 25.5 inches, and we can get the wavelength by using an equation where we multiply the total length by 2 and then divide it by n, in which case our n is 1, which gets us 51 inches. So to find the weight per unit, which we need to find the tension, you essentially would cut up the string and then you would measure it by pounds per inch. And the low E string has a pound per inch of 0.000382216, which refers to this code, which you can find on the website of the exact strings I use. And so now that we have that of the low E, we know that it's the low E, we know that it's this amount of hertz, and that we have this pounds per inch. First, we can use this wonderful equation because we need to find V, which we can get by multiplying the frequency by the wavelength lambda, which, 82.41 hertz times 51 inches is about 4,204.91 inches per second, which refers to this hertz. And then we can find the pounds, which we so you multiply this value that we found, which is the pounds per inch, and you multiply it by the square of this inches per second, which then you can get 6.78 pounds.